All right, guys, last video. All right, so we're going to start out by talking about how we can go about making a non-spontaneous process spontaneous. Because this is actually really important from a biochemistry perspective, because a lot of the processes that are necessary for human life, like production of ATP and stuff, on their own aren't necessarily gonna happen because they have non spontaneous components. But how the body kind of gets around this is it couples non spontaneous reactions with spontaneous ones. Okay? So, like synthesis reactions of proteins and DNA, these are non spontaneous, but before they occur, we metabolize our food, and the metabolizing of our food gives us energy. It's an exothermic reaction that provides the energy necessary for the processes that we actually care about to take place. Okay? So our body's actually pretty smart. It makes the energy and then uses it right away. Now, this is why you have to continually eat, though. You can't just, it's not healthy for you to eat once a day because your body doesn't just like break down a whole bunch of sugar and then hang on to that energy. It does it throughout the day. So it's better if you're eating throughout the day so that you're constantly breaking down that food throughout the day. All right. So we often use the energy released by these reactions to do work, right? So not just with the body, but in regular life, right? The combustion of the gasoline in a car is what drives it forward, right? But the change in free energy represents the energy available to do work if delta G is negative. So, what are we talking about here? We're talking about the fact that in most real reactions, we're not actually converting all of the energy into work. You're going to lose some energy as heat, right? We talked about how delta E equals Q heat plus W work. And so the idea is that the sum of the two is what we're saying is abiding by the first law, in which no energy is created nor destroyed. However, very rarely you convert 100% to work. You're going to lose some to heat. And because of this, it makes our processes essentially not as efficient, right? We don't live in a super efficient world. Like just in this sample reaction right here, look at the efficiency. Yeah, you produced 74.6 kilojoules of energy, but you lost 24.1 to the environment, right? So if we turn that into a percentage, 24.1 divided by 74.6 times 100, 24.1 divided by 74.6 times 100, yeah, that's 33% lost. Not super great, right? But what this also means is that it reiterates what I've been saying before, in the sense that real reactions are not sort of purely efficient. This is why we don't live in a reversible world. We don't live in an efficient world. We live in an extremely inefficient world, which means that our processes are irreversible, which means our processes are spontaneous and non spontaneous, and that is 100% true because we're always going to be losing things to heat and other things. But what this means, though, is that we have been misrepresenting the relationship between delta G and delta G naught. We've been essentially assuming that they're the same, but because of the inefficiency of the reactions we study, delta G only equals delta G naught when we are at standard conditions. So like STP, 25 degrees Celsius, 1 atmosphere of pressure, 1 molar concentrations of solutions, right? We have to be at standard conditions for them to be exactly equal. Most of the time, we're not at standard conditions, though, and we need to use this equation instead. Delta G is equal to delta G naught plus RT, and in this case, the R you need to use is the R with the energy units, 8.314 joule per mole Kelvin, times the temperature, which must be in Kelvin, times the natural log, so that's ln, natural log of Q. And remember Q, this is what we talked about in the equilibrium chapter. Q is the same relationship that K is. It's the concentration of products over reactants. It's just that K has to be at equilibrium. Q could be at equilibrium, or it could be at any other point in that reaction, right? We call Q the reaction quotient. Now, if standard conditions are occurring, then Q is going to be 1, because all of your concentrations would be 1. And I don't care what your, coefficients are, 1 squared is 1, right? Anything raised, 1 raised to any power is 1. So Q is going to come out to be 1. And when you take the natural log of 1, you get 0, which makes all of this become 0. All right, so delta G only equals delta G naught when we are at standard conditions, which means Q would be 1. So if Q is 1, then delta G equals delta G naught. But if Q is not 1, then they are not the same, and you need to use that equation to relate the two to one another, right? And here again just shows you the relationship between Q and K, because I didn't know if you would really remember this. But remember, when Q equals K, we know we're at the equilibrium. When Q is less than K, that means it's a smaller number and it's getting bigger over time, which the only way you can start with something smaller means you have mostly reactants, right? Mostly the denominator, and then you're producing more of the numerator, the products. Or if you start with Q being greater than K, then it's the opposite. We know we're starting with more products, more of our numerator, and we're producing more of the denominator, which is our reactants and our expression. Okay, so it also helps us figure out the spontaneity as far as how the reaction is going to proceed, right? Because if Q equals K, it's not spontaneous in any direction. We talked about this in chapter 15. If Q is less than K, then it's spontaneous in the forward. And if Q is greater than K, then it's spontaneous in the reverse direction. So this is just review from chapter 15, but since we're talking about Q now, I wanted to make sure that you remembered things. All right, so let's look at an example. So calculate delta G at 298 Kelvin for a reaction mixture that contains 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 0.5 atmospheres of ammonia. And we're doing this for the Born-Haber process for the production of ammonia, which is taking nitrogen and hydrogen and reacting them together to make ammonia. All right, so what we need to do here then is it's asking us for delta G, and these are not all 1. So we know that Q's not going to be 1, so Q matters. So delta G is not equal to delta G naught in this reaction. Okay, so we need to use that equation. All right, so this equation, delta G equals delta G naught plus RT natural log of Q. Okay, so let's go down. All right, so delta G equals delta G naught plus RT natural log of Q. Now, right off the bat, we need delta G naught. We were not given delta G naught. So had we been in lecture, this would have been a little bit more obvious, but we solved this at the beginning of the lecture today. You should know what this is. It's negative 33.3 kilojoules. Or no, I'm sorry. We solved this at the end of last lecture. Okay? But this is negative 33.3 kilojoules, and this is from the last lecture. Now, I wouldn't expect you to randomly remember this number. I would give it to you, okay? But I just didn't give it in the slide because sometimes I teach this in the same day, and you would already know it, right? Okay. So, plus R. Now, right off the bat, what do you notice? Delta G naught's in kilojoules. So I would go ahead and convert your R into kilojoules. So 8.314 times 10 to the negative 3. If you write it that way, then it is in kilojoules per mole Kelvin. All right, it says that we're running this at 298 Kelvin. So 298 Kelvin. And then it's going to be times the natural log of some number. But we need to figure out what that number is going to be, right? So Q is equal to the concentration of the products, so the pressure of ammonia squared divided by the pressure of nitrogen divided by the pressure of hydrogen cubed. This is all the stuff we learned from chapter 15, okay? So ammonia is 0.5, and that's going to be squared, divided by nitrogen is 1, divided by hydrogen, which is 3, and that is cubed. Okay, so go ahead and figure out what Q is. So that's 0.5 squared divided by 1 divided by 3 cubed. And I got Q to be 0.00926. All right. So that goes in there. And then basically you just need to plug that into your calculator. So negative 33.3 plus 8.314 e to the negative 3 times 298 times the natural log of 0.00926. And we get that delta G should be negative 44.9. And whether you write this as kilojoules or kilojoules per mole, I would accept it either way. Don't worry too much on the units here, okay? Kilojoules or kilojoules per mole are fine. Is that reaction spontaneous? In the forward direction. Delta G is negative, so the answer is yes, right? Which means it would be non-spontaneous in the reverse. There's another example here that you can work on your own, but it's basically the exact same thing. It's just a different way that you could calculate Q, right? Because different numbers here. So if you want some more practice, you can test this one as well. All right, but last thing we need to do then is if we're talking about Q, we can't leave out K, right? So let's relate Q to K. When does Q equal K? At equilibrium, right? Okay, now what does that mean about delta G though? When we're at equilibrium, Q equals K, and delta G is 0. Okay? So then what happens if I start trying to rearrange these equations, right? So we had delta G equals delta G naught plus RT times the natural log Q. All right, so if we're at equilibrium, then delta G becomes 0 and Q becomes K. All right, so we end up with 0 equals delta G naught plus RT natural log of K. And then you can do some algebra, you can rearrange, so you can subtract this guy from both sides to end up with delta G naught is equal to negative RT times the natural log of K. Or you could rearrange this for K, and K is equal to E, which is sort of like inverse natural log, to the negative delta G naught divided by RT. So basically, what that does then is it allows us to relate delta G naught to K, all right? And that's really important because what we see is there's an inverse relationship. And doesn't that make sense? Because when K is a really big number, what's favored? When K is big, the products are favored. So you should have a negative delta G, right? When K is really small, it's reactant favored. So you should have a positive delta G because it's spontaneous in the reverse, right? So basically, it takes an idea and it essentially gives you a way to mathematically study it. Okay, it's something that hopefully makes sense in your noggin from a conceptual perspective, but how do we look at it from a quantitative perspective? That's what these equations allow us to do. All right, so let's do an example. And I put this in here again, just a graph, so that you can look at what we're saying, but we've already said all this, so I'm just going to move past the graph and get to the example. All right, so estimate the equilibrium constant and the position of the equilibrium for the following reaction at 298 K. All right off the bat, you should be able to answer just from knowing the delta G naught. You should be able to tell me what the position of the equilibrium is going to be. What's going to be favored? You should be able to answer that without doing any math. It's a negative delta G, which means it's spontaneous from the forward. So the position of the equilibrium should favor the products. The position of the equilibrium should favor the products because it's a negative delta G. Now, okay, so we've answered half the question, but now let's do the math and let's actually calculate K. And we can rationalize if our K is correct because we just said that we know it's going to favor the products. So K should be a what? K should be a very big number, right? K should be a big number. Okay, so we know that we should get a big K. All right, so K is equal to E to the negative delta G naught over RT. E to the negative. Delta G is negative 33.3 kilojoules divided by R, 8.314, again, times 10 to the negative 3. Why? Because we need to convert that into kilojoules because, that was per mole too, you got to cancel out your kilojoules. All right? Divide by 298. And if we put that in our calculator, all right, so how do we do the E? Second natural log, so that gives you your E. A negative cancels, so it's just 33.3 divided by 8.314, e to the negative 3, divided by 298, and I get a big honking number, right? A big number. Okay, so if we round that off to sig figs and try to make it a more rational looking number, we get that that's around 7 times 10 to the 5th. And the equilibrium absolutely favors the products. Cool. All right, there's another example on the slide. As always, this one is just there for practice again. It wants you to find K. First of all, notice the temperature is in degrees Celsius, so you need to convert that to Kelvin. Second of all, you weren't given delta G naught. You have to calculate delta G naught from this. Okay? Now, and then so to figure out delta G naught, you got to figure out delta H naught reaction first, and then figure out delta S naught reaction, and then delta G equals delta H minus T delta S. Then you finally get delta G naught reaction, and you can plug it in, solve for the K, yada yada. But what if I were to tack on another question to part A? What if I said, all right, so you've told me K, and you've told me that the equilibrium favors the products, and you know what delta G naught is equal to. What does delta G equal? That's not a trick question. You're at equilibrium, so delta G equals 0. All right, so you can practice yourself with the last question, but that's it. That's it for 18, and that's it for video lectures for this class. I will still give you the notes for the remaining chapters, but that's it for the video lectures. All right, Stover out.